The topology on real numbers we viewed in terms of metrics. But there is another way of viewing that, and that's which gives you the same topology, which is very interesting, and which also generally extends in a different direction from metrics, which is to think of the order on real numbers. Okay, so recall everyone would have seen a partially ordered set, and this is often called poset. So it would be, let's call it S or something. S less than or equal to, okay, is, well, the two parentheses are confusing, so may not do that. So let me just say this is called also poset. S, so it's a set and a relation is a set S with a binary relation less than or equal to, such that, well, it's reflexive. A is less than or equal to A for all A in S. It is anti-symmetric. A is less than or equal to B and B is less than or equal to A exactly when A is B. In fact, it's equivalent, we can say, but well, as you like, because 1 already contains 1/2 of this for all A, B in S, and it's transitive. So this is what you expect for inequalities, not just on reals, but containments in sets. So A is less than or equal to B and B is less than or equal to C implies A is less than or equal to C, this time for all triples A, B, C, and S. And once we have this, we can introduce a notation, or alternatively we could have axiomatized the other way and introduce this as notation. So notation A is less than B if and only if A is less than or equal to B and A is not B. So less than means less than or equal to and not equal to. And this is particularly important in the case we are going to consider now, which is the total or linear order. Total order or linear order. So it's like a line, that's why it's linear as against sets under containment, for example. So total or linear order is a partial order with an additional property such that, let's number it 4 because it continues 4. Given 2 points, at least one is bigger than the other, or the other way around. For all A, B in S, A is less than or equal to B, or B is less than or equal to A. Both happen exactly when A equals B. Okay, so that we can have these things. So these are totally ordered sets. Real numbers are your typical example of these. Okay, so now given these, we have an order topology. So order topology okay, so let's say let x and less than or equal to be linearly ordered. Okay, then a basis, or rather I should say the basis for a topology on X is given by, well, intervals AB, so AB in X. Let me write that out a little more explicitly, what we mean by intervals. By 3 kinds of sets. The set AB, I'll call it, which is defined as the set of all X in X such that A is less than X is less than B for AB in R. AB in X, and while we didn't need it for reals, for general ordered sets, we'll also have to allow consider explicitly raise. So X in X such that A is less than X for A in X, and also X is in X such that X is less than A for X in X. Okay. So why is this a basis at all? We have intervals we have rays and these ways. Well, what happens to the intersection of two intervals? Let's just take a line as an example. So we have a line here. And we have intervals, and we have a bunch of cases to consider, but suppose I take an interval A. Suppose I take an interval which has a point here A and a point B. Okay, so let's look at AB intersection CD. And different colors we'll have it for different cases. So first of all, so let me write something here. What we know is, so we see intersection of basic sets. Well, we need it to be a union of basic sets. Is a basic set. Sometimes it's a basic set, or it's empty. So there are only two possibilities: that it's already a basic set or it's empty. We see this in the real line. Just to see how we use total order just in terms of pictures, I'll say example, if I'm looking at AB intersection CD, and without loss of generality, I assume that A is less than or equal to C. So broadly there are two or three cases, I guess. Well, one of them is if C is here and D is here. Okay, so there could be C and D paired like this, in which case the intersection is going to be this set, which is CB. Okay, C is greater than or equal to B. Then there is a second case where C is somewhere maybe here and D is also before B. So note D is always greater than C. We can ignore the cases where the order is reversed, then it's the empty set. So C is greater than D, but D is itself less than B, then the intersection is CD, the smaller interval. Okay, and then there is a final case where C is already bigger than B, and then of course D will also be bigger than B. So then the intersection is not this set, it's empty. Okay, in the case of rays, we can also similarly look for cases and see. It's an easy exercise. Now we are really using the order topology. We are using the fact that A is either greater than or equal to C, or it's less than or equal to C. So if we switch them without loss of generality, A is less than or equal to C. This is not true with partial orders. Okay, so it's quite easy to see we have an order topology. Also, without trying to prove these things, I will just state a proposition. The order topologies on R and an interval AB in R coincide with the metric topologies. So well, proof is just see that a basic open set in one is open in the other, and for that it's enough to see there's a basic given a basic open set in one and a point. So let's take the real line here. Let's take the real line. A basic open set in the metric topology means I start with a point and I take an interval around it, equal symmetric interval around it. And what you want to say is that there is a open set which contains this point, basic open set which contains this point, and this time it's open in the interval topology. Of course, you simply have to shrink this a little. You don't even have to shrink it. Okay, and how about the other way? The other way around, if I had a red point here and I had an open set in the interval topology, in that case it could be asymmetrical. One point could be close and one point could be much further, but nevertheless we can find a ball contained here. Okay, and all this happens within the open interval, is open in the other, and so essentially we are using the criteria by showing any point is contained in basic open set, let's say call in basic open set W with W contained in V. Okay. Now this looks like the definition of the basic. I'm not spelling this out in detail. We have two different topologies. So if V is open in say the metric topology and we take a point, then you show that there's a basic open set in the interval topology or the order topology. This is also called the interval topology, which is contained in this and contained in V. That is because yeah, you see this by construction. And conversely, given a basic open set in the interval topology, there is an open set in the metric topology which is contained and given a point in this. So given a basic open set in the interval topology and a point in this set, there is a metric ball around it. So a basic metric open set containing this point and contained in the interval. So this will tell you that the open sets, basic open sets in each are open in the other, and hence the collections of open sets are the same. Okay, the reason why I emphasized interval separately. So this whole argument carries through for an interval, but you can have sometimes slightly strange examples, because if I took again the real line and I took the points, we'll take two examples. One of them is I'll take the point 0 and then I'll take the point 1 and then I'll take the point half, and you may guess. So I'll take the point 1 over n. Now whether I took the subspace topology or the restricted metric, which we know is the same, or the ordered topology, 0 is a limit point of these points, 1 over n. On the other hand, if I took the point -1 instead of 0, I took the set excluding 0 but including -1, then in the metric topology it's certainly not a limit point, it is isolated. So also in the subspace topology, which coincides with the metric topology. However, in the order topology, the two sets, so let me write them out here. So example, -1, sorry. So if I take S equals -1 and then or union 1 by n greater than or equal to 1, then -1 is isolated in the metric topology. But as an ordered set, the structure is exactly the same whether you took 0 or -1, because it's less than all of them, that's all. And the relation between them is the same. And so, but not in the order topology. Because you see, if I take any open interval containing 0 or an open ray containing, sorry, the point -1, if I took -1 sits here, if I took any open ray containing this, well, then 0 is missing, remember. So if I took any open ray, it would have to be some point and everything less than that point. But there's always a number smaller than this. So given in the neighborhood of -1, there's a point in it. It's not an isolated point. As I said, that's because as far as order is concerned, then 0 and 1 look just the same. Okay. Fine, so far so good, but the reason we are looking at this, so this is a very important class of examples, and when we look at very large metric spaces or metric space, topological spaces or topological spaces that in other ways are not well behaved, in particular can't be metric, we'll see the order topology examples coming quite a lot. Okay, so but here is the reason we wanted the theorem. But the reason we wanted it here is that a surjective bijective is the relation to homeomorphisms. A surjective strictly increasing function between ordered sets is a homeomorphism. Okay, so if it's strictly increasing and it's surjective, it's bijective. So strictly increasing forces injective. So its inverse is also a function which is also strictly increasing. So if we show that it's continuous, the same argument applies to the inverse. Okay, but the point is just that f inverse of AB is actually equal to f inverse of A and f inverse of B, where f inverse is the inverse function. So this is a bijection, and the reason it is open, so hence is open. So briefly the reason is that the inverse image of basic open sets is a basic open set, and the reason for that is, well, the same argument will go for rays as well. So if I took an interval, well, this is surjective. Strictly increasing means injective, so it's bijective. So f inverse is defined at set level, but because of the order preserving property, meaning because it's a strictly increasing function, you see if a point is between A and B, its image has to be if a image of a point is between A and B, the point has to be between f inverse of A and f inverse of B, and conversely. So inverse image of an open set is open, so this has to be a homeomorphism. Okay, so we can use this as an example. Example is we can construct homeomorphism in either direction, but let's construct it from R to let's take open interval, but just for convenience I'll take -1, 1. But we know that all these things are homeomorphic to each other. Any interval is homeomorphic to, so in construct homeomorphism, I'd say, but I will change that to saying construct strictly increasing surjection. So this is automatically both continuous and has a continuous inverse, and for that we'll take a line. We'll take a line, and let's look at the points on it, which are integer points. So this is 0, this is 1, this is 2, 3, etc. And then I have -1, and then -2, -3, etc. So we have these things, and well, we'll send them to 0, 1, which again I can think of as a little line, not as a line. Let's call that also black. And so suppose this guy is -1 and this guy is 1, and then I'll send the 0 to 0, and I'll send each of these points to a sequence of points. So I'll send n here maps to 1 minus 1 over n, and here similarly -n maps to -1 plus 1 over n. And you can see this is a monotonic function. So the points that are further closer to the origin here are getting closer to the origin, and here they're further away from the origin. So this is strictly increasing, and so well, what happens to the points in between? And it's linear on intervals. So more precisely, so it's the convex linear combination as we used previously. Okay, so this might give you in some ways a nicer, more explicit, more topological construction, because in a general context we may not have the special functions. The special functions are useful. You often transport them from real numbers, and indeed a more elegant version of this would be something like the famous sigmoid function, now very famous because of its importance in, for example, machine learning. So sigma of x is 1 plus 1 over 1 plus e to the minus x. This is strictly increasing because reciprocal flips the order, and then this minus power also flips the order. E preserves the order. So this is, you could also write this as e to the x by 1 plus e to the x, in which case it will take a little more work to prove this is strictly increasing. So here it's clear it's strictly increasing. It goes between -1 and 1. Okay, and its surjective will have to use the intermediate value theorem. You have to use some analysis, while here you can do it more directly by construction. It's just everything is linear. Okay, so the order topology gave us a way Another way, and as I said earlier, we'll see in some context, it gives you a much larger class of topological spaces than metric spaces. Now, not strictly larger, just one that is not contained in metric spaces. So metric spaces are a much larger class, but there are certain directions you can go with order topology that you cannot with metric topology. And order topologies are nice to play with anyway for many other reasons.